You know, we use the internet every single second, but do we ever stop and think about how it really works? How does a photo you send from your phone instantly pop up on a screen halfway across the world? Well, it's not some single file just zipping through the wires. Today, we're going to follow the incredible journey of a single packet to find out.
Okay, so let's start with something that might just blow your mind. That photo you just texted to your friend, it didn't travel as one single complete file. Nope, the internet is way, way cleverer than that. Instead, your device literally shatters it into thousands of tiny digital pieces.
And you can see it right here. It's pretty wild. Your original photo file gets broken down into all these smaller chunks. Each one of those chunks is called a packet. And get this, they don't even have to travel together. Each one can take a totally different route to get to the destination, and somehow they all meet up at the end.
So, let's get to know the hero of our story today, the packet itself. I mean, what is it, really?
A packet is, at its core, just a small piece of a bigger message. All those ones and zeros or bits. But the really crucial part is the header that gets attached to it. You should think of this header exactly like an address label on a package you'd mail. It has all the info needed to get it to the right place and to be put back together in the correct order.
All right, so our packets are all created and addressed. Now they're ready to be sent out into the wild. Let's take a look at what they encounter in the very heart of the internet, the network core. And whoa, here it is. This is the internet's backbone. It's not some single straight line. It's this mind-bogglingly complex web of interconnected, high-speed links and these specialized computers called routers. This giant web is basically the postal service our packets have to navigate. Okay, so the very first rule of the road for our little packet is something called store and forward. What that means is at every single stop on its journey, a router has to receive the entire packet before it can even think about sending it onward. Not a single bit can be missing. The post office analogy just makes this crystal clear, right? A mail sorter has to wait for your entire box to land on their table before they can look at the address and send it to the next truck. Routers are doing the exact same thing, they're just doing it millions of times faster.
Now, our packet's journey isn't instantaneous. Of course not. Just like any trip, it can run into traffic and delays. This is what we're calling rush hour on the data highway. So the big question is, what's causing these slowdowns? Well, there are a few different kinds of delays, but let's start with the most fundamental one, and that's called transmission delay. This is simply the time it takes to push all the bits of the packet onto the wire.
To get our heads around this, we just need to think about two things: L, which is the packet size, and R, which is the link speed. I love this train analogy. Think of L as the length of the entire train, and R is how fast the platform can get that train moving onto the main tracks. And the math here is actually super simple. The time it takes is just the packet size, L, divided by the link's speed, R. So let's see how that plays out with a real example.
So let's say our packet is a 7.5 megabyte chunk of a photo, and our internet connection, the link, has a speed of 1.5 megabits per second. You just do the division. It takes a full 5 seconds just to push that one packet out onto the wire from that one device.
And remember that store and forward rule we talked about? This is where it really comes into play. That delay happens at every single stop. So it takes 5 seconds to get to the first router, then that router has to receive the whole thing before it can spend another 5 seconds sending it to the next one. Just across two links, we're already at a 10-second delay. But wait, there's another kind of delay. What happens if our packet shows up to the party and the router's already busy sending someone else's packet? Well, it has to get in line. This is called queuing delay. And the highway on-ramp is the perfect way to think about it. If cars arrive at the ramp faster than it can merge them onto the highway, you get a traffic jam. The exact same thing happens inside routers. So, our packets dealing with these transmission delays and potential traffic jams, it sounds like chaos. So, with all of this going on, how does the network manage to make smart decisions and actually guide our packet to where it needs to go?
I mean, think about it. With literally millions of possible paths, how on earth does a single router know where to send our packet next? Well, it turns out it's doing two very different but related jobs.
So the first job is called forwarding. This is the local split-second action. A packet arrives, and the router instantly moves it from an input port to an output port. It's like being in a traffic roundabout and just knowing which exit to take. It's immediate. The second job is routing. This is the big picture, network-wide process of planning the best path from end to end. All the routers are constantly talking to each other to build out a map that lets them make those instant forwarding decisions. So routing is like planning the whole road trip, and forwarding is just making the next turn. Okay, Let's zoom back out for a second and appreciate why this whole system, which sounds a little chaotic, is actually a thing of absolute beauty.
So after traveling on all these different paths and arriving at slightly different times, all our scattered packets finally make it home. The computer on the other end looks at that header information on each one and, just like putting together a jigsaw puzzle, reassembles them back into the original perfect photo.
So, why do we do it this way? Why all this complexity with packet switching? Well, it comes down to 3 huge advantages. First, it is incredibly efficient. Links are shared, not reserved for just one person like an old-fashioned phone call. That means lots of people can use the network at once. Second, it's fault-tolerant. If one road is closed, no big deal. Packets just find a detour. And third, it's so flexible. The network couldn't care less if the packets are part of a photo, an email, or a video. It just moves the data.
So really, the next time you send a file online, don't picture some single thing flying through the internet. Picture this instead, a coordinated swarm of thousands of tiny messengers, each one navigating this complex web on its own, all working together to meet up at the end. That is the magic that makes our digital world possible.
But this whole system does bring up a really interesting question. Packet switching is amazing for files, but what about a live video call, where you absolutely need a guaranteed unbroken connection? For that, the internet's pioneers came up with a completely different system called circuit switching, and it works a lot more like that old telephone network, and we are going to explore that in our next explainer.